Hello everyone, we are from Stony Brook University and we are glad to present our work Pixel Motion Diffusion is what we need for robot control today. So for this project, we are going to build a vision language action model. The goal is a single system that can perceive the world, understand instructions in natural language, and taking meaningful actions based on what it sees. This slide summarizes what it actually means and why it's not trivial. A VLA model takes visual inputs like images or videos, combines them with the language command, and output a sequence of actions in the real world. So we are not just doing perceptions or understanding, we are closing the loop all the way to the control. That's also what makes this challenging. We need to align vision, language, and actions, deal with limited data, and connect all the three, and handle long horizon decision making where small errors can compound. On top of that, anything we build has to be robust and safe when it leaves the simulation and interacts with the real world. And a key idea in our approach is that visual motion is a very intuitive interface for robot control. If we imagine an oracle that the cloud directly draws the robot's desired trajectory as on the current visual observations, then a low-level controller's job becomes much easier. It just needs to follow that motion to complete even complex tasks. Actually, there are many previous papers trying to do such a thing. For example, track to act, image to flow to actions, flip, and so on. However, all this works only predicts sparse motion, and they rely on external object detection or tracking methods. The sparse motion may not have enough details needed for the precise control, and the prediction results could be noisy. There is another thread of work that predicts the future RGB frames, and then extracts the optical flow from the predicted frames. But predicting multiple RGB frames is generally challenging and time-consuming. So there, we propose down a two-stage diffusion based framework. The key contribution of down is that we use a pre-trained latent image diffusion model to directly predict the future pixel motion instead of RGB values. This dense, high-quality pixel motion will help the model to generate better robot actions. There are two stages in the down framework. The first one is motion director, which generates the pixel motion from visual observations and language instructions. And the second action expert generates high quality robot actions conditioned on the pixel motion predicted by the motion directors. So to be more specific, the motion director was initialized from a pre-trained latent image diffusion model. The model was further fine-tuned to predict the future pixel motion based on the current visual observation and the language instructions. And thanks to the power of latent image diffusion models, the generated future pixel motion is dense and high quality compared to previous works. And the training does not rely on any robot actions, which could be easily scaled up. The predicted future pixel motion is then processed by a transformer based on the diffusion policy action expert. It is a typical diffusion policy but conditioned on additional pixel motion images and languages. We also found that the pixel motion makes the learning easier. So we benchmark on methods across multiple simulated and real-world environments. On Kelvin, we choose a challenging settings where the model was trained on three sets of task A, B, and C, and then tested on the unseen task set D. Without any external robot data, we achieved sort of performance to many other strong baselines, which shows that John is data efficient, especially with limited benchmark dataset. And here is some kind of rollout examples on Kelvin benchmark, which have the pixel motion overlaid. And we also tested on the meta work, which we also achieved the sort across multiple tasks. Here is an example of the X-arm benchmark. It is single arm table topic and place benchmark, and the robot needs to pick the objects as the language instructed and put into the basket. And we found that down achieves higher success rates with reasonable inference speed. It shows the great data efficiency and could follow the text instructions better. And here is an example rollout of the pixel motion overlaid. Our method is robust to human distractions even. And in this example, you can see that our method it is robust to human distractions while pi0 fails to pick up the correct object. And then, since pixel motion is a general representation, our method also works for bimanual robots. Here, We show that our pixel motion visualizations on Galaxia by manual robots. With the help of the predicted pixel motion, our method achieved lower action prediction errors in the test dataset. And here is the real-world role of the bimanual robot. In these tasks, first the left arm should pick up the toy elephant, and the right arm should pick up the basket at the same time. Then both arms should work together to put the elephant into the basket. With limited real-world demonstrations, our method predicts reasonable pixel motion and successfully completes the tasks. So in conclusion, DAN is a two-stage diffusion-based framework that predicts dense and high-quality pixel motion for robot control. And across multiple simulation and real-world benchmarks, we show that DAN is data efficient and it achieves solid performance. So thank you for the listening.